Hello everyone, this is a video on statistical mechanics where we'll be doing next chapter in the statistical mechanics, that is Ising model. We have done canonical ensemble and canonical ensemble. So this video will be about Ising model. This is a very important question like model and a very important concept that one 5 mark question comes solely in sales and also in JEST the question comes from here and in gate also. So it's very important. So what is Ising model? Ising model Ising model is used to study phase transition in magnetic system. Okay, it's phase transition in magnetic system. So and so how the problem will be asked in this the format of the problem. Let's write the format of the problem. We'll directly jump to the problem because that is what the main thing is. So there are two types of problems. There are two types of problems. First is a structural combination of spins. Structural combination of spins will be given will be given and you have to write and you have to write standard Hamiltonian. That's one way. You'll be given a combination of spins and you have to write the Hamiltonian. Okay, that's one. Another type is instead of structural combination, instead of structural combination, okay, you will be given Hamiltonian of spin system. You will be given Hamiltonian of spin system directly. Okay, okay. So yeah, this is your. Uh, these are the two type of structures that this question will be based on. Hmm. Okay. How the question will be in both the kinds, you can write in both kind of questions, in both kinds of questions. The language of question will contain the language of question will contain the language of question will contain that that there are uh, n spins and each individual spin each individual spin can take si is equal to plus or 1 plus or minus 1, okay, or maybe anything. Okay, so this is how the question will be. Hmm. The Hamiltonian can be given something like this. Just see h is equal to minus summation ij and summation ij si sj, okay, minus b summation si. This can be the Hamiltonian. This is corresponding to mutual interaction of nearby spins. Okay, and this can be corresponding to corresponding to interaction of of individual spin individual spin with external magnetic field B, with external magnetic field B. Okay, so this is what the question will be. Alright, so these are the ways to ask the question. Okay, now we will just do the numericals. We will do just the questions, and from that you will be able to understand how to solve questions related to statistical mechanics, like Ising model. All right, just give me a second. Let me find some questions. Okay, write a question. Consider three Ising spins. Consider three Ising spins at the vertices of a triangle. At the vertices of a triangle. Okay, which interact with each other. Which interact with each other. Okay, with a ferromagnetic ferromagnetic Ising interaction of ferromagnetic Ising interaction of strength J, strength J. Okay, the partition function of the system, the partition function of the system at temperature T is given by where beta is equal to 1 by kBt. It's given by A 2 e to the power 3 beta j plus 6 e to the power minus beta j. Option B 2 e to the power minus 3 beta j plus 6 e to the power beta j. Option C 2 e to the power 3 beta j plus 6 e to the power minus 3 beta j plus 3 e to the power minus 3 e to the power beta j plus 3 e to the power minus beta j. Option D 2 cos h beta j to the power 3. Okay, so these are the questions. Consider three Ising spins are the vertices of a triangle which interact with each other with a ferromagnetic Ising attraction of strength J. The partition function of the system at temperature T is given by this. Okay, just try to solve. See, um, three Ising spins are given. So this kind of questions, how to solve it? When there are three Ising spins given. Okay, so how to solve it? You have to first write the Hamilton. The Hamilton is not given here directly, so you have to write on your own. That is, if this is three, three means S1, S2, S3. If three spins are given, then H will be J, S1, S2 plus S2, S3 plus S3, S1. This is you have to remember. Okay. Hmm. So this is S1. I will do this S2. This is S3, and this will be your Hamiltonian. That is J, S1, S2, S2, S3 plus S3, S1. Okay, is it? So S1 will be 1. We will put 1 1 values here. Like we will put 1 1, like 1 or minus 1 everywhere. Okay, we'll check the combinations. 1 1 1. So this will be what? 3J. 1 1 1 3J. 1 1 minus 1. This will be what? 1 minus 1 minus 1. So only J. Okay, see. This will be 1 minus 1. Minus 1. Okay, minus J. Minus J. Okay, 1 minus 1 1. This is also minus J. Minus 1 1 1 minus J. Okay. Now another combination, if I see minus 1 1. So it will be what? Minus 1 is 1, minus 1 0, minus 1. Okay. This is minus J. So any other combination here will be also minus J, 1, minus 1. This is also minus J. Okay. So, and the final combination is minus 1, minus 1, minus 1. So that is your how much? 1, 1. So this is your 3J also. Okay. So if you see, there are energies minus J. How many times it is repeated? 1, 2, 3, 4, 5. This is 6 times. So degeneracy of this state is 6. G2 6, and G1 is 2, because 3J is 3J repeated twice. So G1, that is G1 is 2, G2 is 6. So what is the question? The question is we have to write the partition function. We know partition function. See, if I can write the thing, E1 is equal to 3J and G1 is equal to 2. It is repeated twice. E2 is equal to how much? Minus J, isn't it? Minus J. And the degeneracy is how much? 6. It is repeated 6 times here. Because this is your energy, isn't it? Hamiltonian is your energy. So the partition function is how much? The partition function is how much? Z is equal to summation I Gi e to the power minus beta ei, isn't it? So if I write it, it will be 2 e to the power minus 3 beta j, okay, plus 6 e to the power minus j, so plus j, okay, beta j, okay. See, let's see if this is in the option. 2 e to the power minus, yeah, this one, option B is the answer. Okay, did you get it? Yeah. First, we have to write the Hamiltonian. It's not given. What is given? Three Ising spins are given. Okay. So if you see here, that is the formula actually. S1 S2 summation plus S2 S3 plus S3. So this is the formula, and using that we'll do this. Okay. Is it correct? Did you get it? Okay. Don't worry. Even if you didn't get it, we'll do more numericals and you will be able to understand. And then we find another question for it. Okay. Next question. Question number 2. Consider a system of two Ising spins, two Ising spins, S1 and S2, taking values plus or minus 1, with with interaction energy interaction energy given by epsilon is equal to minus j s1 s2. Okay, when it is in when it's in thermal equilibrium, when it's in thermal equilibrium at a at temperature T. Okay, for large T, for large T, the average energy of the system, the average energy of the system, the average energy of the system varies as varies as C by kBT. Hmm. C by kBT with C given by the value of C you have to find out with C given by option A minus 2j square, option B minus j square, option C j square, option D 4j. So this is the question. Consider a system of two Ising spins S1 S2 taking values plus or minus 1 with interaction energy given by epsilon is equal to minus j S1 S2 when it's in thermal equilibrium at temperature T. For large T, the average energy of the system varies as C by kBT with C given by minus 2j square, minus j square and 4j. Okay, this is the question. Try this question first. Please try this question first. Consider a system of two Ising spins S1 and S2 taking values plus or minus 1 with interacting energy given by epsilon is equal to minus j S1 S2 when it is in thermal equilibrium at temperature T. For large T, the average energy of the system varies as C by kBT with C given by. Try this question. You can make that table kind of thing. Okay, you have to find average energy. So first, try to find partition function. Otherwise, you can directly get the value of average energy. Okay. How to solve this question? Consider a system of two Ising spin S1 and S2 taking values plus or minus 1 with interaction energy given by this. So energy is given by this. Okay, I will do the table again. See, S1, S2, and the energy is minus J, S1, S2, right? And S1 or S2 can take values plus or minus 1. So let's do it. 1, 1, the value will be minus J, right? 1 minus 1, the value will be J. Minus 1, 1, the value will be J. Minus 1, the value will be minus J. Isn't it? If you do. So the degeneracy of this one is 2. The degeneracy of minus J is sorry, 2. Okay. So The partition function can be written as summation I gi e to the power minus beta I, right? So summation, okay, so 2 e to the power minus beta j, isn't it, g plus 2 e to the power beta j, yeah, e to the power beta j. Is it all right? Is it all right? Okay, so this is your partition function. Okay, what is your internal energy? What is asked in the question? Average energy, sorry, same thing. Average energy, we know what u is equal to, sorry, that is minus del by del beta of ln z, isn't it? Hmm. So let's do it. Minus del by del beta of ln z, 2 e to the power minus beta j plus 2 e to the power beta j. Okay, so that will be minus of, this is 1 by this, so 2 e to the power minus beta j plus 2 e to the power beta j, hmm, and the derivative of it, that's it. So minus the taking, we are taking with respect to beta, that means j is a constant, minus j minus 2j e to the power minus beta j plus 2j e to the power beta j. Okay, this way or other way we can do directly use the formula. Anyway, same thing. 2j, take the minus inside, e to the minus beta j minus 2j e to the power beta j will divided by e to the power minus beta j plus, sorry, plus 2 e to the power beta j, isn't it? So what is the question? Question is saying average energy of the system varies as C by kT for large t. For large t means t is t tends to infinity, isn't it? T tends to infinity. Okay. So how will we introduce t here? We know beta is equal to 1 by kBt. So wherever there is beta, let's put 1 by kBt. So 2j e to the power minus j by kBt minus 2j e to the power j by kBt, okay, whole divided by 2 e to the power minus j by kBt plus 2 e to the power j by kBt. Okay, so this gives me, if I put t is proportional, t tends to infinity, so 2j e to the power minus infinity, sorry, this is infinite, that means the whole thing is 0, isn't it? 0 minus 2j, this is again e to the power 0 whole divided by 2 0 e to the power 0 plus 2 e to the power 0. Okay, how did you get 0? Did you realize? Okay, anyway, okay, there's another way. No. We will do another way. See, here we can expand this e to the power minus x. I can write it as 1, 1 e to the power x. I can write it as 1 minus x plus x square by 2, like that. Otherwise, I can just write 1 minus x. Okay, so I will expand here. I will expand it, so 2j 1 plus, sorry, 1 minus j by kBt. Okay. Okay, let's cancel all the 2's now. 2 to everything will be cancelled out now, all the 2's. So just j 1 minus kBt. Okay. Minus is there in the middle. Minus 1. What is that? 1 plus j by kBt. Okay. 1 plus j by kBt. Whole divided by. Whole divided by. This is okay. Okay, yeah. So one in the below part, 1 minus j by kBt plus 1 minus j by kBt plus 1 plus j by kBt, isn't it? Yeah. All right. So here, if you see, if I open the bracket, that will be j whole into 1 minus j by kBt minus 1 minus j by kBt whole divided by these two. I cancel, whole divided by 2. Okay, here 1 I cancel. What is left? So j into minus j by 2j by kBt. Okay, minus 2j by kBt. So I can write it as minus what? Minus 2j square, and whole divided by 2 is also there, by kBt whole divided by 2. That will be minus j square by kBt. Okay, so that will be your answer. So what was the question? First of all, the question was in place of c. Okay, in place of c we got what? Minus Minus j square. Yeah. So answer will be minus j square. Okay. It's a very easy question again. Here, what we had to do at the end is I expanded e to the power j by kbt as 1 plus j by kbt. This happens when t is very large. Okay, t is very large. This will do. Okay, yeah, e to the minus j by kbt is equal to 1 minus j by kbt. Okay, yeah, that is the answer. Alright, is it correct? Is it clear to everyone? Is it clear to everyone? Let me find more questions. Just give me a minute. Anyway, I'm unable to find any more questions on Ising model, but this is the way to solve these questions. Okay, so let's do more questions on statistical mechanics now. Okay, so we're getting question number three. Mm, In a particular salt, among n atoms, okay, each atom each atom has a spin 1 by 2 and is associated with and is associated with a magnetic dipole associated with a magnetic dipole moment mu b. Okay, the distance between the distance between the magnetic atoms is large enough to make okay to make the interaction large enough to make the interaction between them negligible. Okay, in other words, our system is an idealized spin system. Is an idealized spin system. Okay, the salt is placed. The salt is placed in an external magnetic field. In an external magnetic field B. Okay, find the partition. Find the partition function. Find the partition function of the individual individual atom and that for the solid and that for the solid. Okay, try this question. Very good question. It's not that hard actually. If you read the question, it's not that hard. In a particular salt among n atoms, each atom has a spin 1 by 2 and is associated with a magnetic dipole moment mu b. Huh. The distance between the magnetic atoms is large enough to make the interaction between them negligible. In other words, our system is an idealized spin system. The salt is placed in an external magnetic field B. Find the partition function of the individual atom and that for the salt. Please try. Please try this question. Okay, could you solve it? Sorry, I just got a bit stuck somewhat. Okay, particular salt among n atoms. Each atom has a spin. Okay, so how to solve it here? If you see, our partition function formula is what? What is the partition function formula? ZVT is equal to F summation R e to the minus beta ER. Okay, so here if you see, you'll have energy is equal to minus mu BB for spin half particles and is half and mu BB for is minus half. Okay, is it all right? Why? I've discussed in one of the classes. Suppose this is a spin and the magnetic field is in the same direction as the spin. Then minus of interaction energy is E is equal to minus mu B dot B. This is mu B B cos theta, and if they're in same direction, cos theta is 1, so mu B B minus mu B B. If they're in opposite direction, it will be cos 180 degree, that is minus 1, so that will be mu B B. Okay, for this case and this for this case. So this is it. Okay, so here your partition function will be what? E to the power minus, sorry, e to the power beta mu B B, plus e to the power minus beta mu B B. Okay, this is a single particle. Since a salt contains how many number of particles? N number of particles, and that is here distinguishable. Okay, n number of distinguishable particles, distinguishable particles. So q vt will be how much? Q vt to the power n. Okay, isn't it? Sorry, this is q means your z actually. Don't worry, z. Okay, z. This partition function is taken as z, na? Z vt. Okay, so z v to the power n, that will be e minus e beta mu b b plus e to the power minus beta mu b b to the power n. Okay, yeah, that will be the answer. This will be the answer. Is it all right? Okay, so such a long written question, but it's very easy. To write this question, so no 4 or 5, I think, in 2 dimensions, two metals, two metals A and B have the same have the number density of free electrons in the ratio Na by Nb is equal to 1 by 2. Okay, the ratio of their forming energies is the ratio of their Fermi energies is okay. Try this question. Options are 2:3, 1:2, 1:4, 1:8. So see, two dimensions, two metals A and B have the same have the number density of free electrons in the ratio Na by Nb is equal to 1 by 2. The ratio of their Fermi energies is okay. So the Fermi energy, if you see the Fermi energy is actually related to particle density as particle density. Okay, as how? As EF proportional to n to the power 2 by d. Okay, where d is a what? D is a dimension. D is a dimension. Hmm. So for two dimensions, here it is two dimension. Now. For two dimensions, EF is what? Proportional to n is to 2 by 2. That is proportional to n. Hmm. So here if you see Na by Nb is 1 by 2. So EF will be directly proportional to n. That is EF1 by EF2 or EFA by EFB is equal to Na by Nb. That is 1 by 2. Isn't it? That's clear. That sounds. Is it all like okay? Another question. Question number 5. For non-interacting fermions in d dimensions, the density of states the density of states okay, dE varies as e to the power d by 2 minus 1. Okay, the the Fermi energy EF of an n particle system hmm, in 3, 2, and 1 dimensions will scale respectively as will scale respectively as uh, the options are n to the n square n to the power 2 by 3 n n to the power 2 by 3 n square. So you see n square n to the power 2 by 3. Option D n to the power 2 by 3 n square. Okay, try this question. Non-interacting fermions in d dimensions where the density of states dE varies as e to the power d by 2 minus 1. The Fermi GEF of an particle of an n particle system is a 3 to 1 dimensions in 3 to 1 dimensional scale respectively as this is the question. Okay, try this question. For non-interacting fermions in d dimensions, the NCL states d varies at e to the power d minus 2, d by 2 minus 1. The fermion GEF of one particle in particle system in 3, 2, 1 dimensions will scale respectively as. Okay, see here, if you see, the total number of fermions will be how much? The total number of fermions will be n is equal to 0 to infinity, hmm, Fe Ge D. Okay, yeah, Fe Ge De. So here Fe is what? Fe is your distribution function. Like Fe is equal to, okay, 1 by exponential E minus Ef by Kt, okay, plus 1. So this is our distribution function, and this can be 1 if E is less than Ef, which is a Fermi energy, and 0 if E is greater than Ef. Okay, at 0 Kelvin. At 0 Kelvin. So now G is your what? G is your what? Hmm. Ce d by 2 minus 1. We know it, right? So like G is proportional to e to the power d by 2 minus 1. Hmm. So this whole thing can become, so n can become how much? N can become c 0 to ef here. Infinity is not here. 0 to ef e to the power d by 2 minus 1. Okay, d. Okay, why? Because if you see e is less than ef, e is less than ef, because e is greater than, if e is greater than ef, because okay, I will do it a bit more simply see, 0 to ef something plus ef to infinity something. See, ef to infinity means e is greater than ef. If e is between ef and infinity, that means e is greater than ef. That means if e is 0, if f is 0, this whole integration is 0. So there is no point writing this limit. So we will just write 0 to ef. Okay, and in 0 to ef, if you see, fe is how much? Fe is 1. So only what is left? Ge. And what is the Ge? Ce to the power d minus 2, d by 2 minus 1. Okay, now you got it. Yeah. So this will be uh, c, and this is integration b e to the power d by 2 by d by 2. Yeah, because plus 1 plus 1, so e to d by 2 by d by 2. So if we just see, so n is proportional to e to the power d by 2. Okay, e to the power d by 2. That means e is proportional to, okay, here ef, no? Ef. So ef is proportional to n to the power 2 by 2. Okay, that is what the thing is. Hmm. So what is the question? Question is the Fermi energy of an n particle system in 3 to 1 dimensions. So we have here d. D is a dimension. So in one dimension we have everything all clear. So in one dimension 2 by 1, that is one dimension. 2 by 2, that is two dimension, and 2 by 3 is a three dimension. That's it. So if you see the powers, this is 2, this is 1, and this is 2 by 3. So let's see, 2 1 2 by 3, 2, okay, 2 2 by, okay, okay, 3 2 1, okay, 2 by 3 1 2, yeah, that's the answer. 2 by 3 1, yeah, because 3 3D 2D 1D, this is asked in that order. So 2 by 3 1 2, that will be the answer. Okay, is it clear? Is it clear? Okay, so write one more question. This is a homework. Question number 5. So homework. Question number 6 is a homework. Consider a n. Consider n non-interacting. Consider n non-interacting electrons. N a in a box of sides Lx, Ly, Lz. Assume that assume that the dispersion assume that the dispersion relation assume that the dispersion relation is epsilon k is equal to c k to the power 4, where c is a constant, c is a where c is a constant. The ratio of the ratio of the ground state the ratio of the ground state energy per particle the ratio of the ground state energy per particle to the Fermi energy is to the Fermi energy is the ratio of the ground state energy per particle to Fermi energy is. So the options are 3 by 7, 7 by 3, 3 by 5. Option D is 5 by 7. Okay, these are the options. Consider any non-interacting electrons in a box of sites Lx, Ly, Lz. Assume that the dispersion relation is epsilon k is equal to c k to the power 4. The ratio of the ground state energy per particle to the Fermi energy. Okay, that is the question. Another question, question number 7. A cylindrical at temperature T is equal to 0 cylinder um, cylindrical compartment at temperature T is equal to 0. It's separated into two compartments into two compartments A and B by a free sliding piston by a free sliding piston. Okay, compartments A and B compartments A and B are filled by are filled by Fermi gases Fermi gases made of spin 1 by 2 and 3 by 2 respectively. 3 by 2 spin 1 by 2 3 by 2 particles respectively. If if particles if particles in both the compartments have if particles in both the compartments have same mass, the ratio of equilibrium density of the gas in compartment A in compartment A to that of gas in compartment B is. Okay, cylindrical compartment at temperature T is equal to 0 is separated into two compartments A and B by a free sliding piston. Compartments A and B are filled by forming gas made of spin half spin 3 by 2 particles. If particles in both the compartments have same mass, ratio equilibrium density of the gas in compartment A to that of B is. Okay, so the options are option B 1 by 3 to the power 2 by 5, option C 1 by 2 to the power 2 by 5, option D 1 by 2 to the power 2 by 3. Okay, so please try this question. Okay, please try this question. Like, this is for homework. Okay, these two questions I gave you for homework. So please try these two questions and let me know in the next let me know in the comments how much you got. Okay. Okay, yeah. So that was it for today, and we'll be solving more numericals in upcoming sessions. Yeah, please keep watching my videos. Thank you. Thank you very much.